Have you ever wondered how digital circuits store binary information? Welcome to the fascinating world of digital circuits, where the magic of information storage happens. Our focus today is on two special components of digital circuits known as latches and flip-flops. These devices are the building blocks of memory in digital systems, storing binary information that powers our digital world. Latches and flip-flops are bistable, meaning they have two stable states, enabling them to store one bit of information. This might sound simple, but the implications are huge. This binary information forms the foundation of computing and digital communication. But how do these bistable devices differ? The answer lies in their triggering mechanisms and behavior. Understanding these differences will help us appreciate the unique roles they play in digital circuit design. So, without further ado, let's dive deeper into how these fascinating devices work. First up on our list is the SR latch, a basic memory cell. This little wonder, also known as the set-reset latch, is the most fundamental type of latch capable of storing one bit of information. It's like the building block of digital memory. The SR latch has two inputs: set, abbreviated as S, and reset, shortened to R. Now here's how it works. When both the set and reset inputs are 0, the latch maintains its previous state, a bit like a stubborn mule refusing to budge. However, if the set input is 1 and the reset input is 0, the latch gets a bit of a jolt and sets itself. This means that the output, represented by Q, is 1. On the other hand, if the reset input is 1 and the set input is 0, the latch resets itself and the output Q becomes 0. But hold on, what happens if both the set and reset inputs are 1? Well, this is a bit of a grey area, an undefined state that we generally want to avoid. This is because it could lead to inconsistencies and confusion in the system. Now the SR latch is level triggered. This means that it responds to changes in its inputs as long as the triggering condition is met. While this might seem like a good thing, it can actually lead to race conditions. A race condition is when the output of the latch changes too quickly before the inputs have stabilized, which can lead to unpredictable results. To visualize this, imagine two sprinters racing on a track. If one sprinter starts a fraction of a second before the other, they have an unfair advantage, and the result of the race is compromised. Similarly, in an SR latch, if the inputs change rapidly, the output might not accurately reflect the input state, leading to a race between changes in the input and output. So that's the SR latch for you, a simple yet effective memory cell. It's the starting point of our journey into the world of latches and flip-flops, a world where tiny circuits make a big difference in digital systems. Now let's move on to the D latch, an improvement over the SR latch. The D latch, short for data latch, is a simple yet effective way to store binary information. It's an evolution from the SR latch, specifically designed to avoid the undefined state that arises when both set and reset inputs are at 1. The D latch has two inputs. The first is the data input, commonly referred to as D. The second input is the clock input, denoted as C or CLK. The clock input is crucial because it controls when the data can pass through the latch. When the clock input is high, the latch is said to be transparent. This means that the output directly reflects the input. If D is 1, the output is 1. If D is 0, the output is 0. The latch simply passes the input to the output, hence the term transparent. But what happens when the clock input transitions from high to low? This is where the magic happens. The latch latches onto the input. Whatever the state of D was at the moment of transition, that is the state that gets locked in. Even if D changes afterwards, the output remains the same until the next high to low transition of the clock signal. This design is edge-triggered, meaning it only responds to changes in the clock signal, not the continuous state of it. This key feature eliminates the race conditions we saw in SR latches, making the D latch a more stable and reliable choice for digital systems. So, to recap, the D latch is a type of memory cell that has a single data input and a clock input. It is transparent when the clock is high, passing the input directly to the output, and it latches the input, storing the information when the clock transitions from high to low. It's a brilliant solution to avoid undefined states, providing a clear, unambiguous response to its inputs. The D latch, a brilliant solution to avoid undefined states. Next up is the D flip-flop, a further enhancement of the D latch. Taking a step forward from where we left off with the D latch, the D flip-flop is a marvel of digital circuitry. It retains the same data input D, but adds a clock input C or CLK. and gives us two outputs, Q and Q, the latter being the complement of Q. The D flip-flop is designed to sample the data input, but it does this in a distinctive way. It's not continuously reading the data like the latch. Instead, it waits for the edge of the clock signal. This can either be the rising edge, where the clock signal goes from low to high, or the falling edge, where it goes from high to low. This feature of the D flip-flop is called edge triggering. Why is this important, you ask? Well, edge triggering allows the D flip-flop to avoid the race conditions that we saw with the SR latch. There's no confusion, no uncertainty. When the clock signal changes, the flip-flop samples the data. This makes the D flip-flop an incredibly reliable component in digital systems. But that's not all. The D flip-flop's usefulness extends far beyond its reliability. It's a key player in sequential logic circuits. Sequential logic is where the output depends not just on the current input, but also on a sequence of past inputs. This is the kind of logic that powers digital watches, computer memory, and so much more. The D flip-flop is like the heartbeat of these systems, pulsing in time with the clock signal and sampling the data with each pulse. It's this rhythmic, reliable operation that makes the D flip-flop not just an improvement on the D latch, but a cornerstone in digital circuitry. And so from a simple memory cell, we've evolved through the SR latch and the D latch, and now we've arrived at the D flip-flop. It's a testament to the power of digital design, the way each step builds on the last, leading us to more complex, more reliable, and more useful circuits. The D flip-flop, a cornerstone in digital circuitry. Lastly, let's discuss the JK and T flip-flops. The JK flip-flop is a master of versatility in the world of digital circuits. It's like the Swiss Army knife of flip-flops. Why, you ask? Well, it's because it offers more control over the state of the flip-flop compared to its counterparts. The JK flip-flop has three inputs, JK, and a clock input, often denoted as C or CLK. The J stands for set, and the K for reset. The outputs are Q and its complement Q. The behavior of the JK flip-flop hinges on these inputs. When J and K are both 0, the flip-flop maintains its state, just like our old friend the SR latch. When J is 1 and K is 0, the output Q is set to 1. Conversely, when J is 0 and K is 1, the output Q is reset to 0. But here's where the magic happens. When J and K are both 1, the JK flip-flop essentially becomes a toggle flip-flop. With each pulse of the clock, the state of the flip-flop toggles. It's like a light switch flipping on and off with each tick of the clock. Speaking of toggle flip-flops, let's move on to the T flip-flop, the final character in our flip-flop story. The T flip-flop is the epitome of simplicity. It has a single input denoted as T for toggle, along with a clock input. When T equals 1 with each pulse of the clock, the state of the flip-flop toggles. It's like a rhythmic dance back and forth, from Q to the complement of Q and back to Q again. T flip-flops are incredibly handy when it comes to building counters and frequency dividers, making them an essential tool in the digital systems toolkit. So there you have it. The JK and T flip-flops, truly versatile components in digital systems. Now that we've explored these devices, let's summarize their key differences. Latches and flip-flops, while both storing binary information, differ in their triggering mechanisms. Latches are level-triggered, responding continuously to input given the right conditions. Flip-flops, on the other hand, are edge-triggered, reacting to specific transitions of the clock signal. In terms of applications, latches serve well in memory storage and simpler applications. Flip-flops, due to their synchronized timing, are more commonly used in sequential logic circuits, counters, registers, and other such applications. During triggering, latches can respond to changes in inputs while the triggering condition is met. Flip-flops respond to input changes only during the clock edge transition. In the world of digital circuit design, both latches and flip-flops play vital roles. The choice between them will depend on the specific requirements of your application. And there you have it, a comprehensive look at latches and flip-flops. Remember, the choice between them depends on the specific requirements of your application. Until next time, keep exploring.